morning, good afternoon, good day, good midday, good everything to all of my continents: Asia, Europe, Africa, North America, South America, Australia, Antarctica. I should also mention New Zealand, Madagascar, all of the hemispheres, both of the hemispheres, North and South. Here is Fuji, all of the kitty cats in all of the world. Please do feel extreme welcome here on this live. Thank you, thank you, thank you. Hopefully, many of you will be joining very soon here, both my old friends as well as any new friends who would like to give this live stream a try and listen to what we have to discuss here, which we generally typically discuss kitty cats and physics topics, including but not limited to astrophysics, astronomy, cosmology, physics. And lately, we have been talking a lot about string theory and some of the sort of interesting features of string theory that may or may not be kind of difficult to stomach depending on who you are. So before going too far, let me actually check that this live is working. And also let me share the live on my channel so that people know that indeed we are live and indeed it is happening. So give me 1 second. Let me go to my channel, and if you're joining, thank you so much. Chickpea Break, can you hear me? Thank you so much for joining. Can you hear me? Ver is saying your best mod is here. Thank you so much. How are you? And the live is working. Oh, thank gosh. Thank you so much. So today we're going to talk more about string theory. I also want to take any questions that people have and say hi to anybody who joins. But oh, how nice. Thank you so much. Chickpea Break says, yes, I can hear you. Thank you, Chickpea. Thank you so much. So let me share the live really quickly because I always forget to do that. So we have been speaking about string theory for some time now, for at least a few lives. And one thing I wanted to get done discussing on tonight's live is the reason why it seems to have, it is a dress. You went out, well, I wore the dress for this live. I did go out, but I went to the gym and I did not wear this dress at the gym. So it is you guys that are making the day special, and indeed I am wearing the dress for you. So let's see, can we get 30 likes? Oh, thank you so much. Welcome everybody. Thank you. Thank you, thank you, thank you. Let me pin that. Can we get 30 likes? Can we pin it? Can we see a lot of new people joining? And can we see a lot of old folks joining? And can we see more friends joining? And can we get 20, 30, 40, 4,000 likes? Thank you so very much. So I am telling the channel we are live. Okay, post that. Okay, done. That dress would go nice with the pearls. Oh, thank you. I am currently not wearing pearls, but thank you so much. If there is a pearl sponsor, feel free to send your pearls this way. But also, which pearls are you talking about, Ver? Which pearls? Have you seen me wearing pearls here? Okay, so without further ado, I think I will get started with tonight's topic because we're starting a little bit late and I don't want to spend too long here. I want to go to bed. The earrings. Oh, you're right. Oh my gosh, you remember my earrings better than I do. You're right. I have those like one drop, pearl drop, teardrop type of earrings I have that are pearls. Oh my gosh, wow. Chickpea Break My Mod here knows my pearls better than me. Goodness gracious. Thank you so much for the reminder. Maybe I'll wear it next time with this same dress. Maybe I'll wear the same dress tomorrow. Who knows? So social media Pi says, are you Spanish? I mean, I could be. Who knows? ¿Cómo estás? I know how to say that one in Spanish. I do think that I should get better at Spanish and stop disappointing people who think I'm Hispanic. That is what I would say to that. So Anyways, if you are watching this as a video upload later on, my dear friends, then I would be extremely delighted to, as usual, see your like, share, subscribe, comments, everything that you have to say later on. And also, if you're joining right now, right here, live in the real times, then too, I would love to see any chat messages from you. But what I'll do is I'll get the topic started and I'll do some reading from the book, The Elegant Universe by Brian Greene. And I'll get it going and I'll speak at least for 20, 30 minutes without too much interruption where I interrupt me, because then there will be a nice flow, hopefully, to the topic and people will get some good value out of this video. Okay, so thank you once again so very much for being here. And here it is. So basically, we have been talking about string theory or superstring theory, however you would like to call it. This is something that got started in the 1960s after seeing sort of a bit of a start, if you will, in 1919 when Kaluza and Klein solved the general relativity equations from Einstein, but did something special to it, which is that they added one extra spatial dimension. So we kind of had this predecessor or father or mother or grandmother of string theory happening sort of in the year 1919. And I will tell you right here, right now, and I have said this many times before, that I think the 20th century was a very, 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 very abundant and rich time indeed in physics, with both the relativity theories and sort of certain predictions and results even coming out from that, as well as quantum mechanics seeing sort of leaps and bounds in how well we understood things and how much we saw in terms of deeper insights into these topics in the 20th century, especially in the very early 1900s. The year 1905 was very special, and we've mentioned it a bunch. Even the sort of early 1900s, 1910s, 1920s, all of that was extremely special indeed. Extremely, extremely special indeed. I'm seeing some of the comments. Thank you so much, everybody, for being here. I'm going to say hi to you in a bit. So hang tight and be here for at least 20 to 30 minutes, because then that's when I'll take a break and read all your comments, okay? I'll get to everybody, I promise. So basically, the 1900s were very rich time. And general relativity was something that was developed, of course, after special theory of relativity by Einstein, to, of course, generalize relativity to cover more than just inertial frames, which is what we cover in special theory of relativity. So in order to allow for accelerating frames and give us a more updated theory for gravitation, he developed the general theory of relativity. So as you can imagine, gravitation is, of course, a force or a phenomena that is kind of all pervasive. It kind of affects the universe at a large scale. It's felt by us all. Anybody with mass, any object with mass will feel gravitation. So it's not one of those forces or phenomena, if you will, that goes away if you go large distance. Of course, now I should mention that at very large distance away, there is, of course, also an anti-gravity phenomena going on where the universe is expanding because of dark energy. But all of that is to say, gravitation is very important. And he gave us an updated theory for gravitation, which we kind of can say it's the physics of the large on this side, okay? And then in the same century, we also have quantum mechanics getting developed as well by a number of people, and things like the hydrogen atom, the electron, discovery of the nucleus and subatomic or subnuclear particles like the proton, and then later on the neutron. All of these were also going on in quantum mechanics. And what is more, they started to write down sort of a wave equation for matter. After kind of seeing that light has a wave and particle duality, as in it is both a wave as well as a particle. And in fact, that was given to us also by Einstein. He is one of the fathers of the old quantum mechanics because he gave us the quantum nature of light. And he also won the Nobel Prize for that, for photoelectric effect. So light having both wave and particle duality got people thinking that maybe matter or particles that we consider matter particles may also have a wave particle duality. And they started to write down equations in that way for matter. And then those were developed further. So Schrodinger's wave equation for a particle such as an electron, something small like an electron, and then taking that and taking it further by some other people who also contributed to quantum mechanics, like Max Born, like Dirac. Dirac converted the equations to include relativity, for example. Things like that were all kind of happening at the same time, together simultaneously in the 20th century. Now, the issue was that relativity on this side and quantum mechanics on this side, the physics of the very large and the physics of the very small, were not very well united. In fact, they were not united at all. They did not agree on certain things, and it made life very difficult. So these people probably hated on these people, and these people kind of hated on these people. And the fragmentation that existed between general relativity and quantum mechanics was sort of considered maybe something we just deal with. For example, you might see some of the literature about Niels Bohr. These types of people who worked mostly and focused on quantum mechanics side of things were probably accepting that physics of the very small works at those scales. At the very small scales, you cannot do classical physics. You have to deal with quantum mechanics. You have to deal with uncertainties. You have to deal with the probabilistic nature of the physics, versus at the physics of the very large, such as general relativity. Maybe they should accept that that works at those larger scales, but cannot include things like what we see in quantum mechanics, because there were a number of quantum properties of these particles. More and more particles were getting discovered, but also quantum properties of those particles were also getting discovered, and one of them was spin. Now, why I mention quantum properties is because whatever physics is going to explain, describe, or predict this property, after it's predicted it and it's seen in experiment and it's been verified experimentally, if you are, say, suggesting some other physics or some other theory or some alternative way of seeing things, then you should kind of be able to produce those same properties or similar properties or something that would explain what we see experimentally. So in other words, say these people, classical physics people or general relativity people, and later on the string theory people, let's say these people did not like some of the things about quantum mechanics, and they wanted to come up with a new theory, and we can call that the grand unification theory candidate, right? Because ultimately these people were thinking, why don't we come up with a broader, more general theory, grand unification theory, which can subsume all of the physics that we know so far, including gravitation, electromagnetism, and quantum mechanics. And these people especially did not really like some of the bizarre properties of quantum mechanics. But let's say the GUT people were working on the grand unified theory, but if they could not explain some of the things that were already seen in quantum mechanics, like fermions and how fermions were different from bosons, and that fermions had a different quantum spin than bosons did, spin being one of the properties of quantum mechanics, then that would be really bad. And actually, this is a sort of struggles that the grand unified theory people did face and did have to address in their work. And until you kind of include everything and explain everything that's already known, you wouldn't want to go backwards, right? In your quest to explain everything, if you then explain less things than what's known already, then that is not really good. And people would be very mad. And especially those people who have contributed to quantum mechanics and particle physics. I mean, they should not feel left out or feel like their work is a joke and now people are just throwing it out, and they cannot throw it out because these were experimentally found. If things are a result of experiment, if outcomes are coming out of doing experiments in the lab and they're real and you show the measurements, then you cannot deny them. Whereas there's a bunch of things that are theories which you can kind of deny until you prove them experimentally. So anyways, that's sort of the background in the early 20th century. And remember that people, especially the theoretical physicists, were looking for a grand unified theory. And string theory is a candidate for grand unified theory. It's considered maybe the only real game in town as far as a grand unified theory goes. So even though it wasn't until like 1960s, 1970s when string theory is getting properly developed, actually it was as early as 1919 when Kaluza and Klein took Einstein's general relativity and kind of extended it to add one more spatial dimension. And they were kind of modest because, as you know, string theory has 9 spatial dimensions, with 6 being the extra ones on top of the 3 spatial dimensions that we know and love and are familiar with. So once again, string theory has 9 spatial dimensions, and we will kind of look into as far as like exactly why 9 and why not 8 or why not 7 or why not 15. There is, I believe, we will confirm with the book, I believe there's very math reasons, extremely mathematical or geometric reasons for choosing 9 spatial dimensions for string theory. And also, actually, I should mention off the top of my head, there are quantum mechanics shenanigans reasons for why there are 9 spatial dimensions in string theory. Because remember what I was saying about how when you came up with a grand unified theory or a candidate for a grand unified theory, because really I would say string theory is a candidate theory until there is more evidence for it being a real reality. That is, if it cannot be tested, it would be very hard to really verify it. But it's considered a grand unification theory candidate, okay? Not necessarily a grand unification theory, period. Why? Because for that, we would need to be able to test it. But let's say, because it's a grand unification theory candidate, remember, the most important thing, of course, is that it has to actually subsume what was known so far, which is general relativity, electromagnetism, quantum mechanics. And if there are quantum mechanics things or answers that it cannot get because it, I don't know, kind of sucks at it, then that's not good. Okay. So there were some issues, and it's not the only theory that was sort of struggling with this, by the way. I don't want to be unnecessarily critical of string theory because there are, I should mention, and this book also mentions that there are at least a couple other theories that actually was even worse. They were even worse at giving us the results that we need in order to say, okay, yeah, they are doing a good job of containing quantum mechanics. So now, as you know, quantum mechanics gives us probabilistic answers for things. And probabilities have to be numbers that are between 0 and 1. And if you're expressing it as a percentage, it has to be something between 0 and 100%. In other words, fractionally between 0 and 1. So if you do some things with some mathematics that should then give us quantum mechanics answers, and those numbers are, say, infinities or negative or something that's unallowed, something that's disallowed, something that is not real, cannot be true, in other words, then that's really bad. So something that the theorists, of course, always try to do, like when they're coming up, when they're doing the math and when they're doing all these theories, they have to make sure that they can sort of show us cases of where the answer is known and that their theory should be able to spit out those known things. So they say they're trying to give us some kind of probabilistic answer, which is supposed to reflect something from quantum mechanics, and the number is some infinity, some garbage number, then that means that this theory needs to be worked upon much more. It needs a lot of work. Okay, a lot of work. So, so this was happening in the 1960s, 70s, 80s, where a number of grand unification theory candidates were spitting out sort of these garbage numbers. And so if you continue to spit out garbage, ultimately you will meet with your death as a theory, because people will be like, well, you know what? You're hopeless. Like, this is just not working anymore. And we don't want to keep coming to conferences and seeing talks where the answers are infinities when it comes to probabilities. I'm guessing, I wasn't there in the 1960s, 70s, and 80s. So I am from the 20th century, but I wasn't there in the 60s, 70s, and 80s. So I assume that people were getting frustrated when they kept seeing things to be wrong, or at least wrong as in, if they were promised a grand unification theory, and then that theory gave them answers that are clearly garbage in terms of the quantum mechanics properties that they're expecting, right? So those types of things would have been going on. And so this is my long-winded way to come to basically the question of this live stream that I titled it, why does string theory have 9 spatial dimensions? I want to I will reference the book and we will read from the book as well, but I want to give you my take in short, in summary, before we delve into it deeper, which is that I believe it's really these answers, these infinities or these bad garbage numbers that people were getting. In order to avoid that, was one of the reasons why mathematically they had to use 9 spatial dimensions. When they used 9 spatial dimensions and did the math for 9 spatial dimensions and did the equations for 9 spatial dimensions, then those numbers became much better. They were not getting infinities for the probabilities anymore. So it was a purely sort of math reason for, I believe, I mean, we will check with Brian Greene here from his book, The Elegant Universe, but I do believe that it was a math reason for why they needed the 9 spatial dimensions. So I know that many of you, and indeed many physicists, would not really like that answer very much. Because in physics, we would like for things to be sort of more intuitive. Even general relativity, which was developed by Einstein. Einstein is a theoretical physicist, right? But he didn't include 9 spatial dimensions. He did it for 3 spatial dimensions, the ones that you and I understand, X, Y, Z, length, breadth, and height. So he didn't just do some odd number of spatial dimensions. He did it for 3 spatial dimensions and the 1 time dimension. He did it for 4 space-time. And general relativity, by the way, has sort of a math setup which allows you to extend the dimensions to include more dimensions. So the math setup was such that it was allowed, the math setup, but the intuitive setup was not such that where more than 3 spatial dimensions was allowed. So even Einstein didn't do it. And when he read the papers from Kaluza and Klein where they included the 1 extra dimension, which wasn't even that bad because now we're having 9 spatial dimensions total. So adding 1 more would have made it a 5D theory. So 4 spatial dimensions, 1 time dimension, making it a 5D theory, right? Einstein was still not a very big fan of that, as far as I know. And I mean, he might have warmed up to it eventually. I think it took him like 2 years to sort of give permission to publish that work, etc., when it came to him. So again, if you are sort of struggling with the fact that string theory has 9 spatial dimensions, you're not alone. Nobody would want to really live in a world. Nobody would want to live in a world where their intuition is being sort of attacked or opposed, right? But then string theorists, of course, spend a lot of time in their mathematics, in developing their equations, and they saw that when they include 9 spatial dimensions, which is just the 3 normal ones, the ones we experience, plus the 6 extra curled up little tiny, teeny-weeny ones, then you do good. Then the math checks out. And so imagine if you're working a lot on something to explain everything. It's a theory of everything candidate. It cannot be tested, so we cannot call it a theory of everything. If it were to be tested and if we could verify it, then I could call it the theory of everything. But we have to call it a theory of everything candidate because it cannot be tested as far as I know because we don't have a way to probe those extra dimensions that it requires. Not just mildly suggests, but requires. So this is the struggle of string theory, but also what maybe string theory is proud of, because maybe string theory is saying that, you know what, we have opened our minds to extra dimensions, and maybe you should too. Maybe even though your intuition is saying that there's 3 dimensions because that's what we experience, but maybe we should open our minds to extra small, very tiny, so tiny that we cannot probe that scale yet, teeny-weeny, extremely tiny, curled up dimensions that are sort of little curled up. They're just really snugly and they don't show themselves easily. Maybe there are such extra dimensions. That's what the string theorists are saying. And if you spend enough time doing all this math and it checks out for the 9 spatial dimensions, can you really fault them for believing in 9 spatial dimensions total after you've been, working on it a lot? And finally, you get it to kind of work out, right? So that's the background. That's what these people were doing. So at sort of, if you just hear about it as like a shocking fact, then it might be hard to accept that there are these extra dimensions, or at least to even consider that there might be extra dimensions. But once you kind of see the thought process of these string theorists, you might start to sort of see their point of view a little bit better. And so once again, why there are the 9 spatial dimensions? It's because of math reasons. It's because that's what makes the quantum mechanics answers not be totally crazy. Okay, but do we want a more intuitive way to understand the number 9 here? Is the number 9 just a holy, spiritually guided, divine number that string theory is, requiring? One might ask, and it would be a good question. Okay, so if you are asking that question, just know that you're valid. There is no reason to think that you should just accept 9 like it's, a given. I am not sure that there is an intuitive way of understanding the 9. Okay, I will just be giving you this disappointment right here, right now. It's disappointingly the case that I don't think that there is an intuitive answer for why 9. Okay, why not 15? But I think there's a math answer for why 9, and I think Brian Greene is going to tell us about that in his book, The Elegant Universe, that we're referencing for a few lives now. And so that's what I wanted to tell you in short, and then we'll get into the reading here. And hopefully this is helpful if you're sort of wondering about these topics and you had a question about string theory, and if you had a sort of curiosity about any of this. Sometimes it's good to confirm sort of what we don't know, because if we don't know what we don't know, then that could be also difficult. So if you kind of didn't know, by the way, string theory has 9 spatial dimensions, including the 3 extended ones plus 6 extra curled up ones. So the number is 9. Why 9? It's math. Is there an intuitive answer? I don't think so. So that's what's going on, okay? Let me take some sips of my water. Maybe I'll look at the comments a little bit, and then we will get on with the reading from this book by Brian Greene and see a little bit more about this topic and about the 9 dimensions as is explained by Brian Greene, who's a string theorist himself. And also, by the way, I found a spot in the book. Where we also get a state of string theory, and he mentioned Ed Witten. So I know some people here on the chat in the past have asked about Professor Witten and his work and what he has to say about all this. Of course, he's also a contributor to string theory. So, if you like him, I'm hoping that you also like string theory, because that's what he also contributed to. And we will get a little bit of his perspective as well from this book. Okay, so tonight will be a good night where we discuss both Brian Greene and his words on the 9 dimensions a little bit in just a second here, and then also about Ed Witten. Okay, so again, thank you everybody so much for being here. Welcome so much to the live, and I see all your comments. Really love that everybody's here making friends and talking to each other, and we will acknowledge everybody, and then we will keep going and continue. Thank you so much. And can we get 20 likes and 30 likes? Chickpea, thank you. Social media, thank you. Combat Sports, thank you. Combat Sports says superstring explained by the cutest professor. Oh, thank you. Thank you so much. Steven, hello. SQ Liam says, hey. Hello, SQ. Let's see. Hello, Combat Sports. Why we don't have so much progress in 21st century? Ooh, Combat Sports asked a very nice question. This is a Smarty Foodie Chickpea channel. Oh, thank you. Thank you, Chickpea. So Combat Sports, I don't know if you're still here on the live, but you asked a very nice question. Why don't we have so much progress in the 21st century. You are right. I'll tell you in just a bit my take on that, but I'm a big fan of the 20th century. I will say. Maybe because I'm from that same century, but you are true. You are right. You are right. You are right. But okay, we will also. I'll take that question in just a second as well. I'll tell you. Doro, hello. Stephen, hello. Oh, Stephen asked a good question too. I once heard that dark scientists don't know what dark matter and dark energy is, so they call it dark. Is this true? Um, uh, Not quite. I mean, sort of. Dark, we don't know exactly what dark energy is or dark matter is. They are research topics, so we know some things about them, but they're not um, fully understood, if you will. Dark matter, I can tell you, they call it dark matter because it's basically invisible. This is the type of matter that does not interact with light. And so we cannot detect it with photons, with electromagnetism. So dark matter interacts with gravitation, but it does not interact with electromagnetism. So because of the not interacting with light, we call it dark matter. Dark energy actually had some other names. In the past, in a long time ago, it was actually just called the cosmological constant. And the cosmological constant was actually introduced by Einstein in general relativity as an anti-gravity term in his math. And it's gone, there's a few different, I think there were a few different sort of naming type of things, and they might have settled on dark energy because of sort of the mystery associated with it. But yeah, dark matter, I can tell you it's because of the not interacting with light. Is not Planck the first one who described quantum nature of light? He might be. He might be. I can't remember actually. Um, but Einstein worked on the photoelectric effect. That's what I meant. So regardless of whether more than one person, as in more people, gave us the quantum nature of light, but Einstein is the one who worked on the photoelectric effect. So he was one of the contributors to the old quantum physics, okay? But I totally believe you if you're saying that Planck did something important. I'm sure he did. You can keep the recent ones. Okay, thank you so much, everybody, by the way, for the hearts and things that you're sending. Please do double tap the live and give us some likes. I think I said hi to everybody. Chickpea, Doro, Steven, Combat Sports, Among Limbs, Funny Monkeys. How are you? Um, let's see, anything else? Steven again. Sean. In one of those dimensions, you were a fan of it. What do you mean, Sean? I'm not following. I don't know if I follow what that means. Um, I wish he'd return. Who? Oh, by the way, Stephen, thank you and congrats on your chapter 2. I asked you in one of my comments to maybe send me one of the pages, maybe like written, like typed up, so I can read it more easily, maybe during one of my breaks, during one of my lives. Okay. And for the people who are attending, that is. I talked to him, he's wild. I'll see if he will come back. I don't know what that is about, but okay. Hello, the Bears. Hello, Sean Murphy. Hello, Bobby. Bobby says, I sent you $1,000. Oh, thank you. Where? I hope you PayPal'd me. No more 20 likes. Hello, Bobby. Oh, does someone want to do a super chat? It would be great if you did that. Shame I can't have a proper conversation about physics. I was teacher in one university here, but not able to discuss in English. Oh no! What about Google Translate? Could you say your things in your language and then maybe use a translator? Alfredo Leone, Italian. So could you go from Italian to English in a translation type of way and then still ask your question or give us your comment? Thank you so much, Alfredo. Bobby says hi. Leone. I had a friend like that, friend with that name. Stephen, Alfredo, Stephen. Hello, Ray. Hello, Ray again. Hello, Level Up. Ooh, Level Up says hello from Cincinnati, Ohio. Wow. Hello, Ohio. Blast from my past right there. Heard Stephen's book made Grimmy. Oh gosh. All these dimensions and your mama still takes up all of them at once. Are you saying something about my mother or me? It better be me. Don't go there. Don't go to my mother. She's sort of my daughter at this point. My biological mother, that is. I am my own mom. Alfredo is a friend I met on, gosh, hopefully no boogers are coming out of my nose. Yo mama, he. What does that mean? What do you mean? Alfredo is a friend I met on another stream who's interested. Marinara. Oh my gosh, I actually don't like marinara. I like pesto sauce. Okay, so we will keep on keeping on. We will continue to continue. Everybody, thank you so much for being here once again. And if you have any questions, then put them in the chat. Oh, and I should say, let me answer Combat Sports' question, which was why is the 21st century not as rich in constant physics discoveries and amazing things? And I do believe that is because we are more we're more focused on doing experiments and observations at this time to sort of get confirmations about some of the theoretical predictions. So confirmations of theoretical predictions that were made in the 20th century. So one prime example of that is, of course, the discovery of the gravitational waves by LIGO recently in the last decade. Within the last several years, they started to actually directly measure gravitational waves when neutron stars merge. So from neutron star merger events, or black hole or black hole neutron star merger events. So sometimes these objects are in binaries, a black hole and another black hole, neutron star, another neutron star, or a black hole and a neutron star can be sort of in a binary system, sort of rotating each other, revolving around each other. And they actually release gravitational energy as they do this little dance around each other, and eventually they will collapse into each other. They will merge. They will meet. They will be together, and it actually leads to sort of a cataclysmic, explosive event, very big gravitational event, releasing gravitational waves. And these were predicted by general relativity all the way back in the 20th century, over 100 years ago at this point, because general relativity was established by the time it was like 1916, 1917. So at this point, 2025, and also I think the first year that this stuff happened, observation, it was maybe 2015 or 2016. So around 2015, 2016, 2017, LIGO started to come up with experimental direct observations and direct measurements of gravitational waves. So after 100 years of them being predicted. So in the 20th century, we are very focused on, or sorry, did I say 20th? In the 21st century, the century that we're in right now, in the 21st century, some of you are born in this century. So if you are from the 21st century, what I'm about to say is about the same century. So In the 21st century, the focus is much more on experimenting, on measuring, directly measuring something that was maybe predicted before, observing and becoming better at technologies that help us to observe more. Like, because remember, in the 20th century, before Hubble came and did his things, we didn't even know about other galaxies so much, right? Whereas now we can probe really far, far away. We can probe much deeper into space, and we have so much more technology, so many more telescopes, so much more in space, like, orbiting the Earth, satellites, all of this more. So the focus really has been on technology and building experiments and observatories, or did I say that right? Observatories, observation type of things, so that we can measure things, experiment, and observe better. Because this is where we were lacking in the 20th century in comparison, right? So I would say that's the reason why maybe we don't see as much like path breaking, deep, insightful results come out, because we're sort of in this pause of building the experiments that can do the observations and the confirmations of um, what was predicted. And once we have those done, it's kind of like, okay, this is where we're making the movement. And nowadays, the big results are really the path breaking, like a headline type of news results, are more these experimental confirmations. So they might not seem like as sort of hot and happening, because they're coming from basically their root is in the 20th century. So in that sense, I would say, yeah, the 20th century was a very special time. Lots of really rich contributions were made at that time. And now we spend a lot of time building very difficult experiments and machinery and instruments. And building instruments is also very difficult. It takes time. So if you're building, like, for example, the Large Hadron Collider, right? In France, Switzerland, like that whole CERN experiment, there are so many people that work on that, so many engineers, so many physicists, and people who build that experiment. So you might not be hearing from all of them with some deep insight about physics, but that's because they're busy building an experiment, and that takes a lot of time and a lot of effort and a lot of money, and people are busy writing research grants, proposing uh, to get more money. So honestly, that's what people are doing now, is that they're building experiments or they're writing proposals to get research grants to build experiments to then measure things. Even, for example, the supersymmetry topic that we discovered that we read about and discussed a few lives ago. Even that needs to be confirmed, right? Like, there could be a theoretical prediction or a theory about something that is needed in order to confirm that theory. Even string theory, right, requires supersymmetry. But if supersymmetry is never confirmed experimentally, then it will always remain a mystery. And in order to confirm supersymmetry involves a difficult experiment and efforts to build that experiment, and that just takes time. So partly also um, we don't have a lot of great results as often, maybe because these require experiments to come out with their results, and it takes time to build those experiments and do those experiments. So this is why the 21st century is very, very different. So well noted by Combat Sports, who said that the 20th century was very different. And indeed, in the 21st century, it doesn't seem like we have made as much progress. It seems that way. We've made progress with technology, but we haven't made progress as much with learning deeper and more insights. I don't like marinara. No. Um, it will be a pleasure, although I was a mechanics professor. Maybe quantums is not my best. That's okay, Alfredo. You can still share something from mechanics, maybe classical mechanics, Newtonian dynamics. How about that? Pesto is immaculate. Just imagine pesto on chickpeas. Oh, very true. I share life-changing ideas. Yeah, so if Chickpea Break is supporting me, that's a good thing, Doro. You might want to do the same. Be supportive. or I will not feel very supported. Alfredo, Ondri, and I are good friends on here. I'm her first member too. Oh my gosh, that's right, Alfredo. You might want to join Steven and become a member. How about that? I am starting to add more member-specific content to the channel. So thank you so much, Steven, for becoming a member. Everyone, become a member. Mix of physics and cats. This is the channel of my dreams. Oh my God, Alfredo. I am so glad you found us because it is the channel of your dreams. We cover both kitty cats, kittens, lovely fur babies, babies who are children who are feline, as well as physics, including astronomy, astrophysics, and cosmology, all my favorite topics. I used to have a telescope as a kid. Oh, okay. Okay. So marinara sauce, Alfredo, I don't know if you would approve of such a thing. It's a type of sauce that we put. I don't want to tell you about Italian food. Maybe honestly, Alfredo, our other favorite topic here is food. I eat a lot of chickpeas, so one of my mods has named himself Chickpea. Thank you. Thank you, Coopers and Parkers Fishing Channel. Hello, Coopers and Parkers. Thank you for being here. So, Alfredo, you should tell us something about food because Italian food is my second favorite food after Indian food. Isabel Lauren, hello. Isabel, have we seen you here before? I feel like we have. Oh my gosh. I feel this sounds that name sounds very familiar. Isabel, how are you doing? Grimmy says, Google it. Good night, Grimmy. Um, okay, so I wanted to say hi to everybody. Thank you again for being here. Let me now get into the book. So once again, we were discussing how string theory as a grand unified theory candidate needed to contain both relativity as well as quantum mechanics. And in doing so, it ends up, because of mathematical reasons and because of avoiding shenanigans of quantum mechanics reasons, it ends up needing 9 spatial dimensions, with including the 3 spatial dimensions of XYZ that we all know and love and are familiar with, plus it requires 6 extra dimensions, things that we're not generally familiar with, but these are some small, difficult, or impossible to probe and curled up, if you will, dimensions that we don't generally encounter or experience. But string theory requires it. And we ask whether this 9 number, the 9 total spatial dimensions, has any more meaning. Does it have better intuitive meaning or deeper meaning that we can latch onto? And unfortunately, I believe the answer is no. It's not really very intuitive that it requires 9 spatial dimensions, but it's more of a mathematical reason why it demands it. Okay, as in demands the 9 spatial reasons. Oh, demands the 9 spatial dimensions, not reasons. Demands the 9 spatial dimensions. So we will see more about this from the book The Elegant Universe by Brian Greene, an author and string theorist. So hang tight as we do this reading just now. Isabel says, yes, I have been here before. I hope you're having a great day as well. Thank you, Isabel. Please do enjoy and stay on. So some questions is what he has named this section. First, why does string theory require the particular number of 9 spatial dimensions to avoid nonsensical probability values? Now remember, this nonsensical probability values that he's mentioning here has to do with quantum mechanics. Because string theory as a grand unified theory candidate, like I was mentioning, has to contain quantum mechanics as well as general relativity and give us sensible quantum mechanics answers. If we see it giving us instead some nonsensical probabilities, then that would not be good. And they saw that they need the 9 spatial dimensions. So this is probably the hardest question in string theory to answer without appealing to mathematical formalism. A straightforward string theory calculation reveals this answer, but no one has an intuitive, non-technical explanation for the particular number that emerges. This is what I was afraid of, is that I don't think, like as far as I know, I don't think that there is sort of a non-technical, intuitive, insightful type of reason for the 9 spatial dimensions. I do believe, unfortunately, it's a very mathematical and technical outcome or really requirement of string theory. The physicist Ernest Rutherford once said, in essence, that if you can't explain a result in simple, non-technical terms, then you don't really understand it. He wasn't saying that this means your result is wrong. Rather, he was saying that it means you do not fully understand its origin, meaning, or implications. So Rutherford had mentioned, this is part of the sort of criticism of string theory, is that if you're saying you need this 9 spatial dimensions, but you cannot give a simple answer without doing a bunch of math on the board as to why, then maybe you don't understand it. Now, the author is saying, well, that could be. Maybe they don't understand. Maybe string theorists don't fully understand string theory. It's possible, but that does not necessarily mean that that's wrong. It could just be that they just don't get it fully to the point where they can explain the 9 spatial dimensions in a more intuitive way. Okay? So perhaps this is true regarding the extra-dimensional character of string theory. In fact, let's take this opportunity to brace parenthetically for a central aspect of the second superstring revolution that we will discuss in chapter 12. The calculation underlying the conclusion that there are 10 space-time dimensions, so the 9 space plus the 1 time dimension, making it 10 space-time. So once again, general relativity is 4 space-time with just the 3 space plus 1 time. And string theory, this string theory, superstring theory, is 10 space-time. Okay. So this turns out to be approximate. In the mid-1990s, Witten, so this is Ed Witten, based on his own insights and previous work by Michael Duff from Texas A&M University and Chris Hall and Paul Townsend from Cambridge University, gave convincing evidence that the approximate calculation actually misses 1 space dimension. Gosh. String theory, he argued to most string theorists' amazement, actually requires 10 space dimensions and 1 time dimension for a total of 11 dimensions. So now, after all of the digestion that we had to do about the 9 space dimensions and 1 time dimension, making it 10 space-time, some people are suggesting with their evolved work that it might actually be 11 space-time. Okay, so 10 space dimensions and 1 time dimension. If you're feeling sick of this, just hang tight. We will see what the person has to say about it, okay? We will ignore this important result until chapter 12. So we will just ignore it for now, that in certain evolution of this work, it might even be 10 space plus 1 time. But at that point, honestly, once you've digested the 9 space dimensions, this is already kind of pushing us to open our minds quite a bit. So maybe it's not so shocking that there might even be 1 more. Second, but I will say of everything I've seen so far, it's generally, string theory is generally quoted as having either the 10 or the 11 total dimensions. So it's either 10 space-time or 11 space-time. 1 more may be a thing. Yes, agreed, Alfredo. Second, if the equations of string theory, or more precisely, the approximate equations guiding our pre-chapter 12 discussion. So turns out, here's my Fuji Baba, turns out that in chapter 12, maybe later on, we will consider even 1 more space dimension than what we have mentioned so far. But for now, we will accept this approximation. Hi, Fuji. Hi, 1 second, please. I have a guest who is here to discuss his own string theory. Hi, Shona. Hi, Shona. Hi. I understand you need attention. Good boy. He needs attention. He needs attention. So everything, the world needs to stop right now so Fuji Baba can get attention, okay? Hi, baby. Do you want to hit mama? That's okay. He likes to be loved and then he likes to attack me. Second, if the equations of string theory, or more precisely, the approximate equations guiding our pre-chapter 12 discussion, show that the universe has 9 space dimensions and 1 time dimension, why is it that 3 space and 1 time dimensions are large and extended, while all the others are tiny and curled up? So, this whole situation of the extra dimensions, which is either the 9 space and the 1 time dimension, or the 10 space and 1 time dimension. So it's either a total of 10 dimensions in string theory or a total of 11. But the question also is like, okay, let's say that we've digested the fact that there's 9 spatial dimensions, and then there's this extra dimensions. But how come that 3 of them is the extended ones, like what we experience, the XYZ? How come 3 are extended and the rest, the 6, are tiny and curled up? Like, what is the deal with that? What is the reason for that, right? Why aren't they all extended or all curled up, or some other possibility in between? At present, no one knows the answer to this question. Good God. Hello, Big Frank. So, if string theory is right, we should eventually be able to extract the answer. So, this is also a good point. Again, it's good to know what we don't know, because if we don't know what we don't know, then that would be even worse. So, if you were wondering about how come out of the 9 space dimensions, thank you, Big Frank. Out of the 9 space dimensions, how come 3 are known, understood, experienced, extended, like what we understand and see and feel with the XYZ, or the length, breadth, and height? How come that is 3 of them are extended, and how come 6 of them are curled up? Like, what is the deal with first of all, we don't have an intuitive answer for why 9. We have a mathematical answer for why 9. 9 solves the issues with math. But why are 6 of them curled up and tiny and not some other number and something like that? Okay. Actually, we kind of looked into this a little bit with Stephen Hawking and his book, A Brief History of Time. Remember how he had mentioned something about if there were more than 3 extended dimensions, the universe would be very different. Because one of the things I believe he said was that, remember how he was mentioning how we live in a universe that hosts and supports intelligent life like us. And, the Earth, the sun, our solar system, this galaxy, the rest of the universe developed in this way. And here we are, right? We come from this giant gas cloud nebula thingamawitch, which cooled and condensated to make the sun and the planets. That's how we are here. And then those, planets, including our Earth, actually Earth especially, did a good job of cooling and making oceans and cleaning up its atmosphere so that we can eventually come to be. So he had actually mentioned one good point, which was that if there were even more extended spatial dimensions, that it would really mess up gravitation. And remember how gravitation is a force classically that depends the r, the spatial distance is in the denominator. The force falls off as r squared. So that is the distance between 2 objects, right? So if you had another extra spatial dimension that was extended and contributed significantly to that r, which is in the denominator for the force of gravity, then the force would be even weaker. And so maybe we wouldn't have clumped into galaxies and such in the universe back when the tiny little inhomogeneities of the smooth universe led to having galaxies and large scale structures. And within the galaxies, we started to have stars, and we came to be eventually, right? Like if the sun wasn't, if the stars were not a thing, then we wouldn't be here. If galaxies had not formed, we wouldn't be here. So those types of things, that's one way to look at it as well, is that maybe in this universe that supports intelligent beings who ask the question of why nine, why three space dimensions that are extended and six that are small and curled up, maybe we wouldn't be here in a different universe where those things were differently configured. So, so it's very interesting to consider all this, but why aren't they all extended or all curled up or some other possibility in between? So this is a question that Brian Greene is asking here, and I don't believe that we exactly have an intuitive answer for why, but it is fun to do a thought experiment of what would happen if we did have another extra extended dimension. And I think one of the things that would get affected is gravity. And if we had different gravity, would we even be here? So we'll see. Okay, so let's keep going. Let's see what Brian Greene has to say about this. So at present, no one knows the answer to this question of why the 3 and the 6. 3 extended and 6, what do you call, 6 curled up small ones in the dimensions, right? If string theory is right, we should eventually be able to extract the answer. But as yet, our understanding of the theory is not refined enough to reach this goal. So we can do these thought experiments, but I don't know that our understanding of string theory is refined enough to really give us intuitive answers, okay? That's not to say that there haven't been valiant attempts to explain it. For instance, from a cosmological perspective, we can imagine that all of the dimensions start out being tightly curled up, and then in a Big Bang-like explosion, 3 spatial dimensions and 1 time dimension unfurl and expand to their present large extent, while the other spatial dimensions remain small. Wow. Hello, Eddie. Buongiorno. Good morning. How are you? Yeah. Yeah. For sure. Possible lack of verifiable predictions on the huge number of possible solutions. It can be a mess. Yes. Yeah. So for instance, once again, from a cosmological perspective, we can imagine that all of the dimensions start out being tightly curled up, and then in a Big Bang-like explosion, 3 spatial dimensions and the 1 time dimension have unfurled themselves, but maybe the 6 remain small. The 6 curled up tiny, teeny weeny ones, okay, that we don't experience because and we cannot probe because they're too small, but are needed and demanded and required by string theory in order to be a theory. Who avoids a theory that avoids big bad numbers in quantum mechanics. Hello, Eddie. Thank you. So, can someone do a super chat? That would be most welcome, most appreciated. Rough arguments have been put forward as to why only 3 space dimensions grow large. So why did only 3 space dimensions grow large and the other ones did not grow large? As we will discuss in chapter 14, but it's fair to say that these explanations are only in the formative stages. In what follows, we will assume that all but 3 space dimensions are curled up in accordance with what we see around us. So we don't experience more than 3 spatial dimensions. So we imagine that if there are 9, then the 3 are experienced and extended and big, and the 6 are curled up. Thank you, Stephen. Oh my gosh. Thank you so much, Stephen. Thank you, Stephen. Thank you, Stephen, for the super chat. Anybody else who wants to contribute to super chats are most welcome to do so as of right now. Right here, right now. Go for it. Stephen is a member, yes, and he's doing a super chat. Thank you so much, Stephen. So kind of you. So in what follows, we will assume that all but 3 spatial dimensions are curled up A primary goal of modern research is to establish that this assumption emerges from the theory itself. Third, given the requirement of numerous extra dimensions, is it possible that some are additional time dimensions as opposed to additional space dimensions? If you think about this for a moment, you will see that it's a truly bizarre possibility. We all have a visceral understanding of what it means for the universe to have multiple space dimensions, since we live in a world in which we constantly deal with a plurality, which is three. So even though the digestion of the extra spatial dimensions is difficult, but we already deal with multiple or a plural number of spatial dimensions. We already experience an x and a y and a z, not just an x. We're not one-dimensional spatially. We're not two-dimensional spatially. We are three-dimensional spatially. So because we accepted that space dimensions are more than one, even though it hurts our brain, we can maybe still accept, okay, fine, maybe there are nine and we just don't see the six. But could you imagine if there were more than one time dimension? That would be another whole thing, right? So we all have a visceral understanding of what it means for the universe to have multiple space dimensions, since we live in a world in which we constantly deal with the plurality, three. But what would it mean to have multiple times? Goodness. Would one align with time as we presently experience it psychologically, while the other would somehow be different? As in, would this be sort of a psychological time, and that's different from this other extra time? It gets even stranger when you think about a curled up time dimension. For instance, if a tiny ant walks around an extra space dimension that is curled up like a circle, it will find itself returning to the same position over and over again as it traverses complete circuits. This holds little mystery as we are familiar with the ability to return, should we so choose, to the same location in space as often as we like. But if a curled up dimension is a time dimension, traversing it means returning after a temporal lapse to a prior instant in time, going back to the past, sort of like Back to the Future. This, which is a science fiction movie, I believe. I haven't seen any of them fully, but I am aware of them. So just like Stephen here writes science fiction, you know, these are sort of in line with what we may imagine fictionally, but it's a little strange to think about returning to a previous time. So this, of course, is well beyond the realm of our experience. So we don't experience, we generally don't go back to the past, and we don't go to the future and then come back and all of that stuff, right? So time as we know it is a dimension we can traverse in only one direction with absolute inevitability, never being able to return to an instant after it has passed. Of course, it might be that curled up time dimensions have different properties from the familiar vast time dimension that we imagine reaching back to the creation of the universe and forward to the present moment. But in contrast to extraspatial dimensions, new and previously unknown time dimensions would clearly require an even more monumental restructuring of our intuition. Some theorists have been exploring the possibility of incorporating extra time dimensions into string theory, but as yet the situation is inconclusive. In our discussion of string theory, we will stick to the more conventional approach in which all of the curled up dimensions are space dimensions. Thank God. I mean, as if the extra space dimensions were not difficult enough, right? But the intriguing possibility of new time dimensions could well play a role in future developments. Hello, Courtney. Hi. Hello, my dear. How are you doing? Hi, Stephen. Hi, Alfredo. Hello, Courtney. Thank you, Stephen, for answering some of the questions. Love it. Appreciate you. So, so keep in mind that we haven't seen a too many conclusions about string theory yet. String theory is still considered to be sort of not refined enough where we would conclusively say a lot of things. We have learned certain things that we now know certain things about what we don't know, which is that we don't really have an intuitive answer for why there are exactly 9 spatial dimensions demanded by string theory, and out of which 3 are the extended XYZ dimensions that we all experience, and 6 are the extra small curled up dimensions that are required by the theory but are impossible to probe in real life with experiments as of till date. So we don't exactly know why 9. There is no intuitive answer to why 9, but there are mathematical reasons for why there are 9. We also see that there might be an evolution or a more evolved string theory that actually requires 10 space dimensions and 1 time dimension, making it a total of 11-dimensional string theory. And we will get to that later on. Already, we're dealing with a lot of dimensions here, just with the 10 space time, with the 9 space plus 1 time. And even though we're lacking in the intuition here, because at least we experience a plural of space dimensions, we experience plurality in space dimensions, one could see that maybe one could maybe stretch their imaginations, even though it's not our normal experience, but one could stretch their imaginations to maybe see that, or imagine, not really see, but imagine that there could be some extra curled up tiny dimensions that did not unfurl and become big in the Big Bang when our universe started. So maybe that's a thing that happened. And even though we find it to be a little bit torturous, because we experience plurality in space dimensions, we may just allow the imagination to stretch to 9 spatial dimensions, with the 6 being the extra ones that are small and whatnot. And because they're small, we might even accept, oh my gosh, well, I guess if they're so small and the theory needs them, and the math is good when there's these extra dimensions, and the math is not good when we don't have those extra dimensions, maybe we allow it. But then the author is suggesting that there might even be extra time dimensions that certain string theories incorporate, instead of the extra space dimensions, which would be even more confusing because with time, especially, we experience it in just the one way, one dimensional, going forward in the one direction, starting from the beginning of the universe. And that would be even more confusing. But it might not be something that is totally beyond what people may play with going forward in their work. So if you see something like that, don't be shocked. I mean, we have been shocked enough. Just prepare yourselves. Maybe they will come up with extra time dimensions, because this is all sort of theoretical work that's happening anyways, from the 1960s onwards, because again, we cannot experimentally verify these things. So, do what you will with your theoretical predictions, and especially if they get the money and the research grants to research it that way. So we will see what happens here. Alfredo says, I would be very interested, Ondri, if you could make some time. Chaos theory. Okay, I can definitely make a note of that. We can definitely cover chaos theory going forwards here at some point. And feel free to remind me if I forget or if it doesn't happen soon, okay? Alfredo, you should come to our lives all the time, whenever we go live, and remind me about chaos theory again, okay? Thank you. Grazie. No worries. I lived in the suburbs of Washington, D.C. most of my life, so I grew up with the capitals. Do you worry that the funds spent on string theory has harmed the progress of other testable theories, says SS? So SS, that's a great question. I'm not sure. Of course, I'll try. Only thing is time difference. Well, it's early morning for you now, I guess, and you can always see the live stream upload as a video later on. under the live tab of my channel. So even if you miss the live, you can still see the video at all times later on. It gets uploaded and some people see the live playback. So no worries if you miss the live, you can always see the video later on. So string theory is still sort of on the fringe, as in it's not like it gets a lot of money as it is. So I think that there is merit enough if string theory gets some of the money to do its theoretical work. Because, like, say I was in a very big physics department for my PhD, and there was maybe like one string theorist there, right? So it's not like string theorists are many in number, and it's not like that they get a lot of money. So whatever money that they do get, and maybe they can have a couple of grad students, I think it's fine. I'm not too worried that string theory gets a little bit of money because I don't think that they get that much money actually to do their work. And the people, I mean, the string theorists are people who are very, very good at all of this math. They're very sharp. They are very good at general relativity. They bring other strengths um, to the table. And for that reason alone, I would let them, do their string theory developments and kind of just let it happen because these are some pretty amazing people. And if they're doing good work and it has merit, then I don't mind. I don't mind if they get money. Hi, baby. Hi, Fuji Baba. Fuji agrees. Fuji says that string theory can get money. But of course, if we find reasons experimentally to discard or constrain some of the theories, then I would say pivoting to kind of go towards something that would inform us better is always good. So obviously, I wouldn't want money to be spent on things that are clearly wrong, right? Hi, Shona. So Fuji is now sitting on the book. So I guess we cannot turn the page just now. Michio Kaku got all the money for a long, long time to chase a God equation that probably doesn't exist. Oh, so Michio Kaku, I will say, oh, here's a better thing to discuss. I mean, that's related. Michio Kaku probably got a lot of money because he's probably a very good communicator. So here's what I'll say. It doesn't really matter too much. It's not always the case that the physics that people do is just, the best physics ever and amazing and flawless and the best research ever. Sometimes, if you're a really good communicator and if you can write really good proposals and research grant proposals and communicate and give good talks, is why you will be funded. So Michio Kaku, I mean, we actually read one of his books here on the channel. It's called Einstein's Cosmos by Michio Kaku. So we know that he was into communicating and writing books and all of that stuff. So I feel like if he got a lot of money, it's honestly because in science, the people who communicate and who give good talks and who write good grants are the ones who get the money because the people who are reviewing those grants might not be, obviously, nobody's going to be a bigger expert at the research topics other than the researchers directly. And so, and so somebody has to decide whether you get the money. And if you're a really good communicator, that's how you get the money. So I think honestly, it's kind of, it is what it is. Like Michio Kaku might just be a really good communicator. And he, um, the field kind of benefits from having good communicators who can ask for more money to do the research. Okay, so it goes to show you that there's a lot of there's social sciences that are part of physics as well. Physics is not such a hard science after all. It's not just an objective and clearly logical field as it would like to be seen. There is a ton of psychology and social sciences that are involved in physics, I believe. I'm sure they would love this channel if they can understand something. Who? Who? Hi. Hi, Fuji Baba. Fuji Baba really wants some loving and some attention, and he sat on the book. She's teaching you to stop ignoring me. Here we're open-minded. Who are you talking about, Stephen? Okay, so now let's see a little bit about the state of, so there's one more thing that I wanted to tell you tonight, and then I want to go to bed. So we might actually go into this in more detail tomorrow, but let me read for you a little bit from this part, which involves Ed Witten. So some of you guys, oh gosh, pay him more attention. Of course, yes, of course. So some of you guys have been asking about Edward Witten. So let's look at this part. Edward Witten, one of the pioneers and leading experts in string theory, summarizes the situation. So the situation as in the state of string theory by saying that string theory is a part of 21st century physics that fell by chance into the 20th century. So kind of I think what he means there is the 20th century did not have enough information to really do string theory. But let's see. An assessment first articulated by the celebrated Italian physicist Daniele Amati. Look, we are talking about an Italian physicist now, Alfredo. In a sense, then, it is as if our forebears in the late 19th century had been presented with a modern-day supercomputer without the operating instructions. Through inventive trial and error, hints of the supercomputer's power would have become evident, but it would have taken vigorous and prolonged effort to gain true mastery. The hints of the computer's potential, like our glimpses of string theory's explanatory power, would have provided extremely strong motivation for obtaining complete facility. A similar motivation today energizes a generation of theoretical physicists to pursue a full and precise analytic understanding of string theory. Witten's remark and those of other experts in the field indicate that it could be decades or even centuries before string theory is fully developed and understood. So if you're ready for centuries to pass before we get it, then this is your theory, my friends. This may well be true. In fact, the mathematics of string theory is so complicated that to date, no one even knows the exact equations of the theory. Yes, Baji behind me. Instead, physicists know only approximations to these equations, and even the approximate equations are so complicated that they as yet have been only partially solved. Nevertheless, an inspiring set of breakthroughs in the latter half of the 1990s. Breakthroughs that have answered theoretical questions of hitherto unimaginable difficulty may well indicate that complete quantitative understanding of string theory is much closer than initially thought. Physicists worldwide are developing powerful new techniques to transcend the numerous approximate methods so far used, collectively piecing together disparate elements of the string theory puzzle at an exhilarating rate. So, surprisingly, these developments are providing new vantage points for reinterpreting some of the basic aspects of the theory that have been in place for some time. So, for example, why strings? Why not little frisbee disks or microscopic blob-like nuggets? Oh my gosh. Or a combination of all of these possibilities. As we shall see in chapter 12, the chapter we were mentioning earlier. The most recent insights show that these other kinds of ingredients do have an important role in string theory and have revealed that string theory is actually part of an even grander synthesis currently and mysteriously named M theory. So I guess M for mystery and M for M theory. These latest developments will be the subject of the final chapters of this book. So we will learn more. We will get into this grander scheme later on, but that's sort of the state of string theory right now. Here's the book, by the way, Elegant Universe by Brian Greene. And now I will let you look at some kitty cats and we will conclude the physics part of this live. Please do like, share, and subscribe. And thank you so much for being here and listening to the discussion about string theory. And we referenced the book, The Elegant Universe by Brian Greene. Thank you so much. If you have any questions, please do ask them. Or if you have any comments, please do leave them in the video if you're seeing this as a video later on. Thank you so much and welcome so much to the live once again. And let me know your thoughts. Hopefully now at least we know what we don't know, which is the intuitive answer existing or not about the 9 spatial dimensions requirement of string theory. We learned indeed, we don't know intuitively why that is the case, but we know mathematically that that is the requirement. Okay. Stephen, thank you. Stephen says thank you as always, Andre. Thank you. I used to think Carl Sagan was a great talker. He is. A lot of the popularizers of science, a lot of the popular scientists or physicists are basically people who communicate really well. And those might be the ones that are more famous. Anytime you kind of think that somebody is a famous scientist, they're basically a great communicator. So if you want to be a famous scientist, then make sure that you're a good or great communicator, because that seems to be extremely important. On top of the good science and the great science, you also have to be a great communicator in order to be remembered and known and famous and all of that, recognized and all of that. He hosted the original TV show, The Cosmos. Yes, The Cosmos. And this is our new Cosmos. This is Cosmos by Baji the Handsome Cat and Baji's mom, myself. And this is kind of like similar. So hopefully everybody, once again, thank you so much for being here. Let me show you the situation with the kitty cats. Actually, I think they have all gone upstairs to rest. They might be ready for bed. Ooh, can someone do a super chat? Now is a great time to do that before I leave. SS is talking about thermodynamics. Goodness, that will be a different day when we talk about that. Thermal physics indeed. In fact, SS, why don't you tell us what Boltzmann's constant is? Tell us the value of Boltzmann constant, since you love to talk about thermal physics. Or do a super chat, either or. Oh, Stephen, oh, thank you so much. Stephen has done another super chat. How kind of you, Stephen. Can somebody help out Stephen and do a super chat so that Stephen is not the only one who has to do it? Aw. Stephen! Let me share the live again. Stephen! So by the way, Stephen, are you going to email me one of the pages? If there is a page from your chapter 2 science fiction book that you would want as sort of like a preview into your book or that chapter, instead of trying to read the whole chapter from the Instagram, I could try to read a page and give people an idea. And if you could that would be like a typed up page. So that would also give a better idea for me to read it. I need your email. It's in my bio. Steven. Can you find it in my bio? It's in the bio on my YouTube channel. Okay. I need your email. Yeah. So that would be great. I'm typing in my own chat here. Any other questions, any other thoughts before we wrap it up for tonight? By the way, so we should be back tomorrow. Yes, thanks looking it up. Okay, awesome. Everybody, thank you so much for being here. As always, a pleasure to talk about physics with you, with all of you. And thank you so much for all your chat messages, comments, thoughts, all of that. And we will be back tomorrow. Thank you indeed. And if you want to do